In this video, I'll be going through question 3 from the 2014 exam. We have 3 parts involving writing points as a convex combination of other points and sketching a set and its convex hull. You should refer to the textbook for all of the necessary definitions. For part A, we have to write the point 1, 1 as a convex combination using the points V through to Z. We can approach this in a variety of different ways, but if you have a keen eye, you can spot some shortcuts here. Observe that the x and y coordinates are both the same. We also have 2 points in our list that have identical x and y coordinates, namely V and Y. So we know that the 3 points Q, V, and Y all lie on the same line. Since the convex hull of 2 points is a line, if the point 1, 1 is between -1 and 2, 2 on this line, then by the properties of convex hulls, this means that Q can be written as a convex combination using just these 2 points, and we don't have to worry about the rest. So let's draw it and see if this will work. Note that the drawing isn't required in the working for this question, but it helps in exploring your answer and seeing what works. So let's draw this. The point -1, -1 sits down here, the point 1, 1 sits up here, and the point 2, 2 sits up here. Lo and behold, if we draw a line between 2, 2 and -1, -1, then the point 1, 1 sits on that line. So in other words, the point 1, 1 is in the convex hull of the points V and Y. So that means we know that all we need is these 2 points to write 1, 1 as a convex combination. We can see by inspection that the point 1, 1 is 2/3 of the way along this line. Like this. And so what this tells us is 1, 1 is equal to 2/3 of 2, 2 plus 1/3 of -1, -1. If you're not convinced, we can do the math, but for the purposes of the exam, it suffices to stop there and write the answer as follows. Q equals 2/3 of Y plus 1/3 of V. Let's see what we've just done with a little bit more precision. We've observed that using the points -1, -1, and the point 2, 2, we can write the point 1, 1 as a convex combination of them because it sits in the convex hull of the 2 points, which we know is a line. Before we wrote down the combination by inspection, but if it makes you more comfortable, we're solving alpha times 2, 2 plus beta times -1, -1 equals 1, 1, where alpha plus beta equals 1. This produces the following system of equations. From the x-coordinate, we have 2 alpha minus beta equals 1. From the y-coordinate, we have 2 alpha minus beta equals 1. And from the convex combination condition, we have alpha plus beta equals 1. Since the equations for the x and y coordinates are the same, we can do away with one of them. And this now amounts to solving the following system of equations. 2 alpha minus beta equals 1, and alpha plus beta equals 1. This is an easy one to solve. Just adding them together, we get 3 alpha minus beta plus beta is nothing, equals 2, which implies alpha equals 2 on 3. Since alpha plus beta equals 1, it follows that beta equals 1 on 3, and so Q is equal to 2/3 of 2, 2 plus 1/3 of minus 1 minus 1, as we had before. Now let's do some exploration for part B. What I'm about to do won't be 100% necessary to write on the exam, but it's helpful to understand this so that you can write what you need to write. What we'll first do is see if we need every point that's listed to write Q as a convex combination of these points. So we'll sketch the points and see if the convex hull of any subset contains Q. We're going to have x equal to minus 1 and y equal to 2 for A. B, which is 2, 1, sits here. C, which is 2 minus 1, sits here. And Q is 1, 1, sitting here. And you can see that if we draw a line between any of the two chosen points, we won't hit Q at all. So we know that we need all three of these points to write Q as a convex combination. You could jump in and solve the system of equations given by Q equals alpha times A plus beta times B plus gamma times C, with alpha plus beta plus gamma equal to 1. But there's actually a more efficient method. What we're going to do is translate the points along the plane, in some sense pretending that one of the points we have is the origin. Since we're going to subtract one point from the others, when subtracted from something else leaves a 0 somewhere. It just makes things easier to solve. So if we chose the point C, when we take 2 minus 2, we're left with 0. So let's choose the point C and subtract it from all the other points coordinate-wise. So Q minus C is 1, 1 minus 2 minus 1, which is minus 1, 2. A minus C is minus 1, 2 minus 2 minus 1, which is minus 3, 3. B minus C is 2, 1 minus 2 minus 1, which is 0, 2, and C minus C is, of course, 0, 0. If we sketch these points, we're going to end up with this. For C minus C, we have 0, 0. For B minus C, we have 0, 2. For A minus C, we have minus 3, 3. And for Q minus C, we have minus 1, 2. And you can see that the plotted points are geometrically similar to the ones we started with. So now we can solve the new system of equations given by the following. Q minus C is equal to alpha times A minus C plus beta times B minus C plus gamma times C minus C, with alpha plus beta plus gamma equals 1. This will then be a solution for the previous equations as well. You might like to prove that shifting all the points by the same amount will give you the same solution. The reason we've done this is that the term involving gamma will vanish because of the zeros. So we actually get an easier system of equations to solve. Namely, that given by minus 1, 2 equals alpha minus 3, 3 plus beta 0, 2. Of course, with the condition that alpha plus beta plus gamma still equals 1. You still have to factor in that gamma will add together to make 1, but we don't have to use it when we're solving this particular system of equations. It's not necessary to include all of that explanation in the exam. It suffices to choose a coordinate to subtract and write down the equation you need to solve. We chose C, so we'll write for part B, solve Q minus C equal to alpha times A minus C plus beta times B minus C plus gamma times C minus C. i.e., and this time I'll write it in matrix form, 1, 1 minus 2 minus 1 equals alpha times minus 1, 2 minus 2 minus 1 plus beta times 2, 1 minus 2 minus 1. And of course, since C minus C is 0, we don't have to include that part. We also require that alpha plus beta plus gamma is equal to 1. So we'll continue up on the top of the page. This gives us, using the top part of the matrices, we have 1 minus 2 is minus 1, equals alpha minus 1 minus 2 is minus 3, and 2 minus 2 is 0. So that's equation 1. And using the second row of the matrices, 1 minus minus 1 is 2, and we have that that's equal to alpha times 3 plus beta times 2. This implies alpha equals 1 on 3 by equation 1. Then 2 gives 2 equals 1/3 times 1/3 is 1 plus 2 beta, and then from there that implies beta equals 1/2. Finally, from the fact that alpha plus beta plus gamma equals 1, we conclude that gamma is equal to 1 minus 1/3 minus 1/2, which implies gamma is equal to 1 on 6. So we conclude part C by writing, so Q equals 1/3 of A plus 1/2 of B plus 1/6 of C. Let me move the answer over here, but don't forget there's some working involved, and we'll move on to part C. For part C, it really helps to have a ruler when you're sketching the convex hull, and make sure you pay attention to everything that's written in the set. So what we've got is a set of points determined by some formula and some inequalities on x and y, and a single point on its own. Note that x has to lie between pi and 2 and 2 pi, so when we draw our axes, we only really need to consider the positive side of x. Let's mark the points 2 pi. For our convenience, we'll mark pi as well, and pi on 2. So we know that our points are going to lie between this part of the graph. We also require y to be less than or equal to 1. So let's mark the point 1. And then we'll draw a straight line from the point pi on 2 to 2 pi. Finally, we want y to be greater than or equal to sine x. So let's draw that in. When x is equal to pi on 2, sine of x is equal to 1. When x is equal to pi, sine of x is 0. We'll go down to minus 1, so let's mark that as well, and then back up to 2 pi. Let's draw this in. We're not too stingy on this. As long as it looks close enough to a sine curve, we'll be satisfied. Finally, we want all the points greater than or equal to sine x, so we'll shade in the gaps. And of course, we've got this last point left over. We've got the point 0, 5 on 4. So mark the point very clearly and write in its coordinates. We've just sketched the set V as defined there. And now separately, we want to draw the convex hull of this set of points. So let's draw in our axes again. Let's mark off some of the extreme points from the graph we have. So of course, we're going to need 2 pi. There's a good chance we'll need this point here, which is 2 pi 1. Let's mark off the point 0, 5 and 4. And let's draw this line in here. Let's draw in part of the curvy part of the sine graph. But here we have to be particularly careful. Let me just show an example on the previous graph. We know we have to draw a line from any point in the convex hull to this point 0, 5, 4. If we draw it from this local minima directly to the point, but still got a bunch of points in this bump that haven't been included. So we have to be selective about where we choose to stop drawing our sine curve so curvy. It's not too crucial that you get the point exactly right. It looks like it should sit somewhere around here. So let's just keep drawing the curve sort of round and then stop and then draw a straight line from that point to 5 on 4. As long as it's clear that the curvy portion of the sine curve remains, you'll get the appropriate marks. And then of course from that corner over here, we want a line directly from there to the point 5 on 4. And we want all the points in between, so let's fill that in. And that finishes up this question.